Hey friends, it's Ben again. This is a quick video for the differential calculus class. The topic here is, well, this is really by special request. Somebody asked me to do another example where we had exponentials and we did something with concavity. And that seems like a super reasonable sort of thing, especially because there's kind of some trickiness going on with your exponentials. Okay, so I've got a problem worked out here. Well, I've got a problem, and we will work it out, and let's see how that goes. All right. So sharing screen and screen mirroring. Yay. Okay. I used to have a lot of problems with getting that to work, and it seems like it's working a little bit better here lately. All right, so the function that we're going to deal with is this one here. We've got x squared plus 5x, the whole quantity times e to the minus x. Now, I purposely on that, oh, please don't tell me you're going to, that is super frustrating because I prepared my example ahead of time and so that you wouldn't have to watch me type this in. But this is a quick graph of the same thing. And now we've got that. All right. I'm going to hide the extra stuff here so that we can kind of expand it out. Now, what we're really looking at is talking about the concavity on this. And I do not have a pointer on the iPad, so hopefully you can see the pointer of my mouse. You can see that somewhere down around in here, the concavity changes. So somewhere between -2 and 1 probably. And then somewhere between 1 and 2, the concavity changes. So it's kind of curving down in this part here, but it's curving up on the left end. It's curving up on the right end, okay? So in order to see that, or see where exactly those happen at, we're going to have to do some derivatives. And doing those derivatives gives us an illustration of using the product rule and using the chain rule. So my f prime of x here, I'm going to go through these and take the derivative of the first factor and have 2x plus 5 e to the minus x plus, now I'll leave the first part alone, x squared plus 5x plus 6, and then the derivative of e to the anything is just that thing, but the chain rule says we have to take the derivative of the stuff inside of that. The stuff inside the exponential is the minus x, and the derivative of that is -1. So it will be helpful here if we factor out the e to the, pardon me, the e to the minus x from everything and be left with the 2x plus 5. And then we've got to distribute that -1 and have minus x squared minus 5x minus 6. I'm going to go ahead and rewrite that as e to the minus x times minus x squared minus 3x and then -1. Okay. So now for getting our f double prime of x, we're going to take it and like before, just identify our two factors. We'll take the derivative of the first one, so you get e to the minus x, and then times -1, and you leave the minus x squared minus 3x minus 1 alone, plus, now we'll leave the e to the minus x alone, take the derivative of the polynomial, and you get minus 2x minus 3, okay? So if you factor out the e to the minus x again, notice that we have a -1 that we need to distribute through, And conveniently enough, everything that we're distributing through to already have it in minus. So this will become x squared plus 3x plus 1. And then we'll have minus the 2x. And then we'll have minus 3. So that means we have e to the minus x times x squared plus x, and then minus 2, okay? Now, since we're talking about concavity stuff, we're setting the second derivative equal to 0. If it was increasing or decreasing, we'd set the first derivative equal to 0. So now when you set these equal to 0, an exponential can never be equal to 0. If you look at the graph of an exponential, it goes down towards 0, but it never actually gets there. So the part that made it 0 has to be here. So I'm going to take and factor that into x plus 2 times x minus 1 equals 0, and get x equals negative 2 or x equals positive 1. So that means that we're thinking about our number line, and our cutoffs are at negative 2 and positive 1. Those are the critical values where we might be changing concavity. And we saw from the graph, we already had an idea that these changes of concavity, these inflection points, were around there. But now we're just going to figure out some x values to test this at. And you always pick just the easiest x values you possibly can for it. All right. Now I will need another page to finish this off real quick. But I think I'm going to grab this piece here, copy it, and add another page. Paste this. All right, and I'll move it around a little bit here. And say that was f double prime of x. All right. So, figuring out f double prime of negative 3, f double prime of 0, and f double prime of positive 2. Okay, so we just have to plug in here. E to the minus 3 is e to the positive 3. So that's going to be like 20 or so. Okay, and then you'll have to say minus 3 squared. Remember, when you square a negative, it will become positive. Minus 3 minus 2. So we'll have 9 minus 5. So we'll have 4 e to the third, and that's positive. And that means we've got something that is concave up in that region. So f double prime of 0 is e to the minus 0, so it's going to be just 1. And then you'll have 0 squared plus 0 minus 2, so you end up with a minus 2. That's negative, and that means it's concave down, okay? And then f double prime of 2 is e to the minus 2, so it's going to be like, I don't know, 0.1, 0.2, something like that. And then 2 squared plus 2 minus 2. So you'll end up with 4 e to the minus 2. So I don't know exactly what it is, but it's positive, and that means it's going to be concave up in that area. So we have to think about where it's increasing, not increasing. Doofus, what was I saying? Concave up, man. And where it's concave down, okay? So since there's only one region where it's concave down, that's maybe the easiest thing to think about, and that's around x equals 0, and it expands out in either direction and gets cut off at minus 2 up to positive 1, okay? So then for the other regions, we have to think about this one where x was -3. That's this area here. And it gets cut off at -2 and then goes forever to the left. So we'll say minus infinity up to -2, parentheses, union, parentheses. And now the other piece of that is here around x equals 2, and that expands to where x is +1, and then it continues on forever off to the right. So +1, infinity. If you want to write positive infinity to just help you remember it's positive, that's fine. But that's really what we're looking for an answer here. Okay. I need to have that be a rectangle, and it wasn't quite. All right. All right then. So that gets you an example using exponentials where you're having to figure out concavity. The main thing that this is coming up with is that your exponential is always going to be positive. So it's something that you'll end up factoring out. Then additionally, the derivatives of your exponential are always going to be the same, except the chain rule might put a minus in there or some other multiple if you don't have just a plain old e to the x. So consequently, when you're doing these problems that have concavity questions and they involve exponentials, a major portion of it still ends up being the concavity question about a polynomial. It's just that the polynomial gets kind of generated and affected by the exponential. Okay. All right. So hopefully that's a good example. And I will talk to y'all later.